This is topic 2 in Unit 2, the addition rule of probability. So in the last topic, we got to know probabilities as much as we possibly can without calculating too many of them. So we talked about notation, interpretation, and how to construct probabilities. Before we just get a new rule handed to us, I would like to take a little bit of time, and you'll need to do this on your lab learning quiz as well. So I would definitely make sure you go through this one. I want to just explore this a little bit instead of just having the rule straight out stated. So we're going to start with a question where we again roll a die, which is very common in probability because everybody knows how to roll a six-sided die. Everybody knows that there's 1, 2, 3, 4, 5, 6 for the outcomes. What is the probability that you roll a 2 or a 5? So there's one way to get a 2 and there's one way to get a 5 out of 6 possible outcomes. So 2 out of 6 is our fraction, which reduces to 1/3 or 0.3333. If you had called this 0.3 with the line over top, meaning repeating, that would technically be a more accurate answer, and I wouldn't favor 4 decimal places over the line on top. I would probably treat them as pretty equal. So that's up to you. That's more of a style thing. But I'm always going to round to 4 decimal places. So the question is the probability of 2 or a 5, is that the same thing as the probability of a 2 plus the probability of a 5? So these are going to seem like they're always going to be similar, but you are probably maybe guessing that it's not the case. So there's one way to get a 2 out of 6 outcomes. So that's going to be 1 out of 6 plus one way to get a 5 out of 6 outcomes. So that's again 1/6. This is 2/6, which reduces to 1/3, which is again 0.3333. So now let's answer our question here. Is the probability of 2 or 5, is that equal to the probability of 2 plus the probability of 5? And in this case, that is a yes. But I'm going to pose a side question here. What is the probability that you roll an even number or a multiple of 3? So even number, even numbers are 2, 4, 6, 8, 10, 12, and so on. Multiples of 3, 3, 6, 9, 12, 15, 18, so on. But we're looking at only a die roll. So when the question asks the probability of an even or a multiple of 3, there are 4 possible ways that we can do that. So 2, 4, 6, and then multiples of 3, 3, and 6, and we've already counted that 6. So we just say that there's 4 ways out of 6 that we can get an even number or a multiple of 3. This reduces to 2/3, which would be very careful, rounds to 0.6667. So if you were doing the line on top, you wouldn't need to have anything at all with the 7. If you answered 0.6666, that would technically be incorrect. So you want to indicate that you're cutting the number off, but it's closer to the higher number than it is to being rounded down. However, is the probability of an even or a multiple of 3, is that the same thing as the probability of an even number plus the probability of a multiple of 3? So again, even is 2, 4, 6. So there's 3 outcomes that satisfy that out of 6 for our total possible in our rolls, plus 3 and 6 are our multiples of 3 out of 6 total, which ends up getting 5/6, which is 0.8333. So the question, are these equal to each other? The answer to that is no. So when you get a question posed to you that says, what's the probability of one or the other, you can't find them separately and sum them together unless you take one thing into account, which you may have already guessed here. So the question is, what was the problem with the right side? Why did that not end up being equivalent? So that's what the question is posed right here. Why aren't they equal? Well, I'm sure you were just dying for a visual here. So the first one, probability of 2 or 5. The red numbers are what qualifies out of 6. With the second one, the probability of 2 plus the probability of 5, we have a 2, we have a 5, and we put them together. But over here, the probability of an even or a multiple of 3, so the numbers that qualify this, if I said, hey, what are the numbers that are even or multiples of 3? You got 2, 3, 4, and 6. So that's 4 possible numbers out of the total that satisfy this statement. But when you get to this last one over here, the probability of an even number plus the probability of a multiple of 3, well, you may have already guessed, but what happens is you end up double counting this 6. So the consideration that we have to take for every single time that we do a probability that has an or statement with it is to consider the overlap. And we'll formally phrase that, but for now, that's what you want to be thinking about. So now that we've gone over the reason that we can't just add two probabilities when they have the word or in between, the official rule using official notation is P of A or B is equal to the probability of in a single trial event A or B occurs. And then again, a trial is some kind of part of an event. So it could be flipping a coin, it could be taking a class, anything at all that you're interested in looking at the probability of. The rule is really close to what we looked at in the previous slide, but it's the probability of A plus the probability of B minus the probability of A and B. Probability of A and B is the overlap that we had seen with the 6. So if there's an item that's in both set A and B, then we'll count it twice and then take it out once. So the way that I suggest that you look at this is either you use the formula exactly how it is, or you just don't double count. So different people like to do this different ways. I prefer just to not to count the overlap because then I'm kind of seeing if my answer makes sense rather than just plugging it into the formula, but that is still okay too. So another term that we need as we move on with this section is mutually exclusive. So that word overlap that we had mentioned is that was brought up in the addition rule. Two events or more are mutually exclusive if they cannot occur at the same time. And this is also called disjoint. So everything on this slide can also be referred to as disjoint. So this would be an example of the probability of a 2 or a 5. So they couldn't occur at the same time, so technically they'd be separate parts of the event. However, when we looked at an even or a multiple of 3, that 6 was what occurred in the overlap. So when we subtract off the probability of A and B occurring at the same time, we're taking away that overlap. When we look at an example coming up, this will be a lot more clear, but for now, all of these terms are kind of general and we bring them together when we do get a chance to practice. So here's another example of mutually exclusive. So on the left, there is a deck of cards, aces and kings, and you can't be an ace and a king at the same time if you happen to be a playing card. However, if you're looking at the event of a heart or an event of a king, a card can be a king of hearts. So the event on the left is mutually exclusive because they cannot happen at the same time. Whereas on the right, they are not mutually exclusive because you can be both a heart and a king. So one more piece before we start some practice is complementary events. The complement of A consists of all of the outcomes in which event A does not occur. Originally, this sounds like a pretty useless statement, I think, but we're actually going to use the complement a lot. So it's kind of a visual concept, so that's how I recommend that you look at it. But the more we use it, the more clear it will become. The notation on this is actually pretty varying depending on where in the internet or textbook you are. The notation we're going to use is P of A bar. So just like how we had X bar was the sample mean, A bar. So it's that, just calling it a bar, that line on top. The way that you would read this is the probability of A complement, or the probability of the complement of A, or A bar. Other ways you might see it is A with a little apostrophe. So that's pretty common too. I'd say it's probably about 50-50. So by definition, you either are A or not A. So for example, if you were rolling a die, if A was a 2, then not A would be everything that isn't a 2. So 1, 3, 4, 5, and 6. So if you added up the probability of something and its opposite, or something and everything else besides that something, then it's every single possible outcome. By definition, all complementary events must be mutually exclusive. And here are two images. So let's say this would be heads and tails. So if event A was flipping a heads, then A complement would be everything that isn't getting a heads. And I'm assuming that we can't have the coin land on its side. Well, I'm sure it's technically possible, but pretty improbable, so we won't include that in here. So A bar is going to be getting tails. So the second sample space over here doesn't have to be 50-50. It can be any different division of 100% at all. So let's say A was getting a 2. A bar is everything else but, so that would be 1, 3, 4, 5, and 6. All right, so let's get a chance to practice some of these. We'll bring a lot of them together, and we'll continue to use these concepts as we keep on going. So the table below has a study to compare the health of those on the AHA diet, the American Heart Association diet, to those on the Mediterranean diet. So the American Heart Association diet was the diet that was a little bit higher in carbs, less in fat and meats. There's a lot of research going on around with that diet. And the Mediterranean diet is more like a paleo, like a whole foods kind of thing. So this table breaks up people into what diet they were on. So the AHA is the top row, the Mediterranean is the bottom row. And then within that, it has whether or not they were diagnosed with cancer, fatal heart disease, non-fatal heart disease, or if they were deemed healthy. So we're going to use this to answer the following questions. So find the probability that one randomly selected person is on the AHA diet. So what you need here is, again, it's part over whole anytime we make these fractions for our probabilities. So we need to know how many people were on the AHA diet over how many people were participating in total. So there was 303 if you add across here on the AHA diet, and then there was 605 total. So when you divide this in round, that's a little bit over half. And then 303 is a little bit bigger than half of 605, so that seems like it's a reasonable answer. I do always encourage you to ask yourself, does my answer make sense? If you ever get a probability that's bigger than 1, definitely you have to check into that. And we'll see in a little bit. There are some things that will come up on your calculator that will look like it's bigger than 1, but it's actually notation. So this is where we're going to start to talk about our addition rule here. So B says find the probability that a person is healthy or has cancer. So when you think about the addition rule removing overlap, well, here are the healthy people, and here are the people that have cancer. So if a person had cancer, we wouldn't deem them as healthy. So what we'll find is that there'll be no overlap when we use the formula. So by the rule, the probability that the person is healthy or has cancer, that's equal to the probability that they're healthy plus the probability that they have cancer minus the overlap, which is the people that are healthy and have cancer, which in a realistic sense would be nobody. So when you find these totals here, there's 512 out of 605 that were healthy. 22 out of 605 had cancer, and then again there was 0 in that overlap. So what you might do is, if you're just saying, hey, I'm going to see all of the things that qualify, so healthy or have cancer, and just not count overlap, you may actually just start with this fraction here. But again, that's completely up to you. Everybody is comfortable with something different, and I think both ways are equally as good. If you are using the formula, I would just try to, make sense of the values instead of just, plugging numbers into the formula, which is pretty easy to do once you've written down the formula. So this is a 0.8826. So 88.26% of these people were healthy or had cancer. So next, find the probability that a person is on the Mediterranean diet or has non-fatal heart disease. So with this example, we will see that overlap that we saw in our first example. So there are 7, 14, 8, and 273 total together on the Mediterranean diet, and there are 25 and 8 with non-fatal heart disease. So if we added these up separately, found these probabilities separately and added them together, then we would end up counting these 8 people twice, but there's only 8 people here, there's not 16. So what the formula will do is it will add the probability of the Mediterranean diet, the probability of those with non-fatal heart disease, and it will subtract out those 8 people that were counted twice. Or you can also just skip right to the fraction here and just count up 7, 14, 8, 273, and 25 without double counting. So it is up to you either way. This is a 0.5405 probability, which is 55.05%. So next, let's look at the mutually exclusive. A random selected day that is a Tuesday or a randomly selected day that is raining. So these events can occur at the same time. So you can have a Tuesday that is raining. So these are not mutually exclusive. A day can both be a Tuesday and raining. B, state if the two events are mutually exclusive, a randomly selected day that is Tuesday and a randomly selected day that is Friday. These are going to be mutually exclusive because a day can't be both Tuesday and Friday at the same time. So complete the following for the event. There is a 30% chance of rain. So there's going to be a few questions that go along with this one. So first, state this event as a probability using proper notation. Describe the complement of the event. Using proper notation, state the probability of the complement. So first, the probability of rain equals 0.3. So you have to convert the 30% to a decimal, but other than that, it's just converting and then combining in the notation that we've been getting used to. So describe the complement. So the complement is everything that is not rain. So in this case, it is not raining. There's going to be some foggy ground, like if it's, kind of misting, what would we include? So anything there's water coming out of the sky, I would call that rain. And the opposite of that would be that it does not rain. And then finally, using proper notation, state the probability of the complement. There's a few different ways that you can write this. So you can either do the probability of rain bar, which I am personally, I wouldn't prefer this one as much because it doesn't describe what exactly you're thinking is the complement. But if you said P of does not rain, the person that, is seeing this will say, hey, okay, it's the complement of this is does not rain, or this is the probability that it does not rain. So you're not leaving any guesswork to the person, but technically this one is correct too. So it either rains or it does not rain. So these two are going to be 100% of your total possibilities because it's either one or the other. So this is going to be 70% or 0.7. So we have one more of these. This is accurate as of around 2009. FBI data shows that 62.4% of murders are cleared by arrests. So the same 3 questions to begin. State the event as a probability using proper notation. Describe the complement of this event. This one is going to be a little bit more detailed than the previous slide. And then using proper notation, state the probability of the complement. So first, the probability that the murder was cleared by arrest, so probability cleared by arrests, is 0.624. So that needs to be converted to a probability because the percentage is not. So the probability that it is not cleared by an arrest can actually be a number of things. In class, we usually discuss this for a bit. So this could be an unsolved crime. This could be, I mean, even if somebody turned themselves in, I would consider them being arrested after that. The person that committed the crime could be known and deceased. So that technically wouldn't be cleared by an arrest, I don't think. Um, so, I mean, we can call this not cleared by arrests, but it's always important to ask yourself, well, hey, what does this actually mean? And finally, you can use the complement notation, but again, I do think that it's best for all involved to just like explain what your probability is actually describing. So the probability that the murder is not cleared by arrests is going to be 1 minus 0.624. So they're either clearing it by arrest or they're not clearing it by arrest. There's no other options because not clearing it by arrest includes everything else that can possibly happen. So this is a 0.376 probability. Okay, so that wraps up the addition rule of probability. I would definitely go through and practice these without the PowerPoint in front of you just to get an idea of how you're doing. And as always, feel free to email me if you have any questions.